Hello, Year 9. This is Chapter 8b, titled Perfect Squares and the Difference Between Two Squares. So just a couple things to think about. We know that a square is a shape where all four sides are the same length, all right, and 90-degree corners. Fantastic. So if we have a perfect square, that means if one side is 5 centimeters, that means the other side is going to be 5 centimeters. So when we talk about a perfect square as a number, we're talking about 5 being squared, or we're talking about the number 25. So a couple perfect squares could be 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9, 4 squared, which is 16, 5 squared, which is 25, and so on and so on. So any perfect square just means the same number multiplied by itself. So in other words, 5 squared is actually 5 times 5. And we look at it as 1, or the final answer, the product, which would be 25. So that same idea is going to transfer now to binomials. So if we had a binomial squared, a binomial might be x minus 2 squared would equal something, who knows what, but we're more worried in this left-hand side at the moment. So just trying to simplify, any binomial multiplied by itself, so we'd have to recognize that x minus 2 squared is the same as x minus 2 times x minus 2. Because once we write it like this, we can apply our expanding that we did in class yesterday. All right, so then we can actually expand it out, and we can get an expression in expanded form. Then you also have something where you've got the difference of two squares. So the difference of two squares would be, let's say, for example, if I took a perfect square like 4 squared, and I subtracted another perfect square. So let's say, maybe I'll just use x for that. Basically what I'm saying here is if 4 squared minus x squared, what winds up happening is, if I think back through the process, and we're not quite coming up with this ourselves yet, but to get the 4 squared, it's 4 times 4. So remember when we expand, it's the first term times the first term. So 4 times 4 makes that 4 squared. And then to get x squared, that's x times x. So again, we've got one arrow, which takes us from 4 times 4 to get 4 squared. And then we've got x times x, which makes x squared. But the problem is, usually we also wind up multiplying 4 times x, and we also multiply x times 4. But neither of those are represented in this difference on the left-hand side. So what winds up happening is we get one with a plus and one with a minus, so they wind up canceling out, and we don't get that middle term. So what we'll look at in a moment as well is how if we have two binomials, they look identical, except one has a plus and one has a minus, then we'll look and see what the pattern is there. Okay, so we're going to treat them the same as we did yesterday with expanding the brackets, but you'll notice some common themes throughout as we go through the examples. So let's look at example 1 to start. This one says expand x plus 3 squared. So we're going to use the distributive law. We're not going to use the box method, which was like your Punnett square that we did in method 1 yesterday. We're just going to go straight to distribution. So what we'll say is if we've got x plus 3 squared, my next line of working will be to rewrite it as x plus 3 by x plus 3. Because when you square x plus 3, that's what it really means, x plus 3 by x plus 3. So now I can take my arrows and I can say, all right, I'm going to distribute the x to this x and to the 3. I'm also going to distribute the 3 to this x and to the 3. So we've got x by x, which is x squared. We have x by 3, which is 3x. We have 3 by x. And then we have 3 by 3. So we get our final answer of x squared plus 6x plus 9. All right? In our second set of examples, we're going to do the same thing. So we're still going to use this distribution method, However, notice we've got a slight difference. They look like they're the same binomial, but one has a minus, one has a plus. So let's see what happens when we actually expand these. So x by x by 5, negative 5 by x, negative 5 by 5. Let's see what happens. So x by x is x squared. X by 5 is 5x. Negative 5 by x is negative 5x. And negative 5 by 5 is negative 25. So what we should notice is that these two middle terms that we usually add together, positive 5x and negative 5x, they are going to wind up making 0. So we only are left with x squared and minus 25. So my final answer for this one is going to be x squared minus 25. Go ahead and pause the video here and try the next two on your own. Give yourself some space and then push play and you can check to see if you got the same answer. All right, guys, once you finish trying these on your own, go ahead and check that you got the same 4 terms when you expanded, 3 minus x times 3 plus x, and then the two middle ones cancel out, and then the same 4 terms when you expand a minus 10 times a plus 10, and then again the two middle terms cancel out. So they add to make 0. Therefore, we don't include them in our final answer. So just going back over some common themes. Notice when you have, this is called a difference of squares because you've got one with a minus and one with a plus, and you always wind up with a minus. And both of these two terms are perfect squares. So 100 is 10 by 10. A squared is a by a. 9 is 3 by 3. X squared is x by x. X squared is x by x. 25 is 5 by 5. So we have a difference, because they're being subtracted, of two perfect squares. So that's why we come up with the title difference of squares, okay, or difference of two squares. They always wind up, if you notice, you've got the same two terms, one with a plus, one with a minus, you're always going to wind up with the squares with a minus between them. If we go back up to our first example, you'll notice that when you take the same exact binomial and copy it twice and we multiply, x plus 3 times x plus 3, you wind up with x being squared. You wind up with 3 being squared, but then the middle term actually is a double because it's 3x and 3x twice. So that's where that comes from. So it's actually twice of that first term times the last term, okay? Or the middle terms multiplied together. So couple themes where if you see a problem like this, you could go straight to your answer if you notice what exactly is going to happen here. All right, guys, in this example, it says that a square of side length x. So we start off with this original square where all the sides are the same and the side lengths are x. So it's x by x. And now we change it, so one side is reduced by 1 unit and the other side is increased by 1 unit. So now it looks more like a rectangle. Oop. And we've got one side is increased by 1 unit, so x plus 1. The other side is decreased or reduced by 1 unit, so x minus 1. Find an expanded expression for the area of the resulting rectangle. So we know that the area is length by width. And we want the resulting rectangle, not the original. So we're going to take our length, which is x plus 1, multiplied by the width, which is x minus 1. And when I multiply that out, notice we have a pattern. We have an x and a 1, but one has a plus, one has a minus. So let's think back. This was our perfect, was it a perfect square or was it a difference? This was a difference of two squares. So we know we're going to get the first term squared minus the second term squared. So my guess is we're going to get x squared minus 1 squared, but let's see if that actually happens. So x by x, the first term times the first term is x squared. X by negative 1 is negative x. 1 by x is x. And 1 by negative 1 is minus 1. Negative x, positive x makes 0. So I wind up with x squared minus 1. So we were correct in our hypothesis if you just follow the pattern. Part B is asking you to decide, is the area of the original square the same as the resulting area for this rectangle? Explain why or why not. So let's look at the original square for a moment. The original square, the area would just be side by side, right? X by x. So x by x is x squared. So that's the original square's area. And then our resulting rectangle area wound up being x squared minus 1. So do these two shapes have the same area? No, they do not, because the area of the rectangle is actually reduced by 1 unit overall. All right, so we would have to answer by saying no, they do not have the same area because, so let's grab our cursor here. All right, no, these two shapes do not have the same area. The area of the resulting rectangle is 1 less unit than the square. 1 less squared unit, we'll say. All right? So we do actually have to write out a full answer for that and explain why or why not. So we have to explain why they are not the same area. All right, guys, great job going through an applications. Go ahead and try the ones from the book, and then you can watch 8C for the second half of the lesson.